Hello everyone, this video is going to cover sections 4.6 to 4.10 in the textbook, and we're going to keep going with continuous distributions. So far we have talked about in general about continuous distributions, and we specifically focus on the uniform distribution and the normal, which is also called Gaussian distribution. And I did mention that this is probably the most important distribution in the whole class. If you recall the graph for the normal distribution, which is a bell-shaped curve, and remember, for any distribution the whole area is always equals to 1. Notice that here the values for x or c or y, whatever you want to call it, well, let's go with y, can be positive and can be negative, okay? But the area obviously is always going to be positive. The gamma distribution, which we're going to talk about in this section, has a skew distribution. As you can see from here, from the domain, the smallest value is 0. And there are multiple cases where distribution like this can be very useful to model specific situations. For example, the length, okay, of time between malfunctions for aircraft engines. This is one case, aircraft engines. Another instance where you have a distribution similar to this, it will be the length of time, okay, length of times between arrivals at a supermarket. Supermarket. Okay. So these are just two. There are more examples where the gamma distribution would be very useful to model these things. Now, formally, we say that a random variable y is said to have a gamma distribution with two parameters, alpha and beta, if and only if the density function is given by this. Notice that here it doesn't say that alpha and beta have to be integers, but if they are, life will be easier. So this is the density function, which, remember, this implies, because this is going to be very useful, that the integral from 0 to infinity of y to the alpha e to the minus y over beta to the alpha, and then the gamma function, which is defined by this integral, that this has to equals to 1. Now let's look to the gamma function. So let's focus on the case where alpha is an integer, in particular if alpha is a number more than or equals to 1, and we will have the following. So let's start with alpha equals to 1. So if alpha is equals to 1, then gamma of 1 will be the integral from 0 to infinity of y to the 0 e to the minus y dy, which is minus e to the minus y from 0 to infinity. So this is 0 minus 1, and you can check that it's equals to 1. Okay. If alpha is equals to 2, then this will be gamma of 2, which will be the integral from 0 to infinity of y e to the minus y dy. We did this integral before. You did it in calculus 2 multiple times, so you do integration by parts. Using integration by parts, you will end up with this minus y e to the minus y. You should check these integrals. Again, this is from calculus 2, and you should check that this is equals to 1 again. Let's do one more. You wanted to find gamma of 3. And this will be the integral from 0 to infinity of y squared e to the minus y dy. And again, once you do all the integration by parts, this is actually equals to 2. So therefore, if you keep going this way, then gamma of alpha is going to be equals to alpha minus 1 factorial if alpha is an integer. So notice how this is also technically equals to just so this is for integers, and in general this will be alpha minus 1 times gamma of alpha minus 1, because you notice n factorial is equals to n times n minus 1 factorial, or n times n minus 1 times n minus 2 factorial, and so forth. Right, so it's very important that you know the definition of the gamma function. So this gamma function, if it is an integer, is just equals to n minus 1 factorial. Now, we know that the gamma distribution is a random variable, so therefore it has to have a mean, and it has to have a variance, and therefore a standard deviation. All right, so but I recommend you again to memorize these values, but let's see how you derive it. Remember that the expected value of y, which is the same thing as mu, by definition is the integral from 0 to infinity of y times f of y. But in our case, f of y is y to the alpha minus 1 e to the minus y over beta, divided by beta to the alpha, and then gamma of alpha dy. Okay? So if you combine these two, then this will be the integral from 0 to infinity of just y to the alpha e to the minus alpha over beta, divided by beta to the alpha, and then gamma of alpha dy. Now notice, and I mentioned this already, we know that the integral from 0 to infinity of y to the alpha minus 1 e to the minus y over beta to the alpha, then the gamma function, that this has to equals to 1 because it's a density function. So therefore this implies that beta to the alpha and then the gamma function has to equals to the integral from 0 to infinity of y to the alpha minus 1 e to the minus y over beta dy. Okay, so it's just manipulating this. We're going to need this right now, so that's why we wrote it like that. Alright, so therefore here you can take out the 1 over beta to the alpha gamma to the alpha times, now we have the integral from 0 to infinity y to the alpha e to the minus y over beta dy. Therefore, if we use this result right here, notice that if this is just alpha, then this will be alpha plus 1. Okay? So therefore that will give us beta to the alpha plus 1 times gamma of alpha plus 1. But from the definition, remember gamma of alpha plus 1, it will be just alpha times gamma of alpha, from the definition we just have in the previous page. So therefore this will be 1 over beta to the alpha omega alpha times beta to the alpha times beta, and then times alpha omega, not omega, gamma alpha, sorry. And you can see here that this will cancel, and the answer will be alpha beta, which is what we needed. Now in a similar way, you can find the the expected value of y squared, and then you use the formula of the variance is the expected value of y squared minus the expected value of y squared to figure out the variance. And I believe that may be one of the homework problems. Now the next definition is a very special case of a gamma distribution, which is used a lot in statistics, and it says the following: let nu be a positive integer, then a random variable y is said to have a chi-square distribution, which, like I just mentioned, is very important in statistics, with v degrees of freedom if and only if y has a gamma, only if and only if y is a gamma distributed random variable where alpha is equals to nu over 2 and beta is equals to 2. In other words, the density function for this particular case will be equals to y to the nu over 2 minus 1 e to the minus y over 2, and then this will be 2 to the nu over 2, and then it will be gamma of nu over 2, which again, this is only true between 0 and infinity. Right, so notice therefore the book calls this a theorem that if you have a chi-square distribution, notice that the mean, since this is gamma, the mean is supposed to be alpha and beta, which in our case alpha is nu over 2, beta is 2, so therefore the mean is nu, and the variance, remember, is equals to alpha beta squared, so in our case this will be nu over 2 times 2 squared, which will give you just 2 nu. So when you take the second part of statistics, which I believe is math 381, this distribution is going to be used a lot there. And again, since this is gamma distribution, the graph looks something like this, where you only have positive values. And you will see also later that a chi-square distribution is technically just a normal distribution squared too, but we'll get to that later. Now, we have one more definition here. We will get another distribution from the gamma distribution, and it's the following: a random variable y is supposed to have an exponential distribution with parameter beta if and only if the density function is this. Notice here that the value for alpha is equals to 1. So therefore the exponential is a density function where alpha is a gamma density function where alpha is equals to 1. And therefore the mean is going to be, remember, alpha beta, which in this case will be 1 times beta, just beta. And the variance, remember, is alpha beta square, which will just be 1 times beta square, or just beta square. Now, if you recall from chapter 4, there was one distribution, well, in particular the geometric distribution, that have something that was called a memoryless property, and this was the only discrete distribution that had it. Well, the exponential distribution has the same property in the continuous world, and is the following. So this is an important example that will make calculating exponential probabilities pretty easily. So let's say that y is exponential with obviously the only parameter is beta. So what's the probability that y will be greater than a plus b given that y is already greater than a? Okay. So if we use the conditional probability formula, this is supposed to be the probability that y is greater than a plus b and y is greater than a. divided by the probability that y is greater than a. Now we have done this multiple times before. Remember, the probability that y is greater than a and b and greater than a is the same thing as the probability that y is greater than a plus b. And the bottom obviously is just y is greater than a. Okay, so then notice I'm going to do the two separately. The probability that y is greater than a plus b, by the definition of exponential, it should be from a plus b to infinity, or 1 over beta e to the minus y over beta dy, which is the following. You can take out the 1 over beta, and this will be the integral of that. It will be minus e to the minus y over beta times beta from a plus b to infinity. So the betas cancel, so this is minus. We put infinity here, this will be 0, and then this will be e to the minus a plus b over beta, with the minus sign here, so this is equals to just e to the minus a plus b divided by beta, which you can rewrite like this: a over beta, b over beta. Now, in a similar way, you can show the probability that y is greater than a. This is just equals to e to the minus a over beta, so we did that already. So therefore, if we plug all of this in here, we will end up with e to the minus a over beta times e to the minus b over beta, e to the minus a over beta. Notice that this will cancel, and this will be e to the minus b over beta only, okay? Which by definition is the probability that y is greater than b. Okay? So this shows the memoryless property of the exponential distribution. All right, so now let's do an example. The magnitude of earthquakes recorded in a region of North America can be modeled as having an exponential distribution with mean of 2.4 as measured on the Richter scale. Find the probability that an earthquake striking this region will exceed 3.0 and part B between 2 and 3. Okay? All right, so since this is exponential and the mean is 2.4, that means that beta is 2.4. So therefore that implies that the density function is going to be equals to 1 over 2.4 e to the minus y over 2.4 dy. So for part A, the question is asking what's the probability that y is greater than 3. So this is just the integral from 0 to infinity of 1 over 2.4 e to the minus y over 2.4 dy. Now the integral of this is going to be minus, or it's just going to be, minus, it should be 3 e to the minus y over 2.4 from 3 to infinity. So this will be minus e to the minus infinity, which will give you 0, and then minus e to the minus 3 over 2.4, which is just e to the minus 3 over 2.4, which is around 0.2865. Part B is asking the following: what's the probability that it will be between 2 and 3? So this is the integral from 2 to 3 of the same density function, which is equals to the same thing as part A. You just have to change the limits of integration. So it will be now from 2 to 3. So it will be minus e to the minus 2 over 2.4 minus e to the minus 3 over 2.4. And this is around 0.1481. All right, let's try another example. Let's say we have the following density function where this is only valid between 0 and infinity. So part A, what value of k will make this a density function? Remember that all we need to show is that the integral is equals to 1. That is the integral from 0 to infinity of k yq e to the minus y over 2 dy has to be equals to 1. All right, so notice you can integrate the whole thing, which can take a little bit of time because you have to use integration by parts 3 times, or you can see that this is clearly a gamma distribution. Okay, so clearly this is gamma, where you can see that, well, beta is equals to 2 and alpha is equals to 4. Why? Because 4 minus 1 is 3. So therefore, that implies that k has to be 1 over gamma of 4 times 2 to the 4 power, which this turns out to be 1 over 96. Why? Because remember, this is 3 factorial, and this is 2 to the 4, which is 16, and 16 times 3, sorry, times 6 is 96. So that's the value of k. Okay, so let's go to part B. The question says that y has a chi-square. Remember, the chi-square is a specific case for the gamma distribution. If so, how many degrees of freedom you have? Well, let's see if this is the case. Well, recall from the previous page that to be chi-square, alpha has to be equals to nu over 2, and beta has to be 2. Well, clearly, beta is equals to 2, and we have the alpha is equals to 4. So therefore, if we solve for nu, that means nu is equals to a. So the answer to part B is yes. Nu is equals to a, and this is the number of degrees of freedom. Okay. Part C is asking what is the mean and what is the standard deviation. Well, remember the mean is equals to alpha beta. So in our case, alpha is 4, beta is 2 is equals to a, which is just nu anyways because it's chi-square. And the variance is equals to alpha beta square, which in our case will be 4 times 2 squared. So this is 16, but that's the variance. So that means the standard deviation is the square root of the variance, which is just 4. All right, so that's it for section 4.6. Let's go to 4.7, which is the beta distribution. Section 4.7, the beta distribution. Let's start with the definition. A random variable y is said to have a beta distribution with parameters alpha and beta positive if and only if the density function is given by this, where b of alpha beta is called the beta function and is defined to be this. Notice that it's very important to realize that you can define this as a product and quotient of gamma functions. These are the same gamma functions that we used in the previous section. Again, since this is a random variable, it obviously needs to have a mean and a standard deviation, or mean and variance. So the mean, which is the expected value of y, is equals to alpha over alpha plus beta, and the variance is equals to alpha beta alpha plus beta squared, then alpha plus beta plus 1. All right, let's derive the expected value, which is very similar to what we did in the previous section. Remember, by definition, this is the integral from 0 to 1 of y times the density function, which in this case is just y to the alpha minus 1 minus y to the beta minus 1, and all of this divided by the beta function, okay, dy. Again, you can take out this part out, and you multiply these two. Notice that the ones will cancel. So this is 1 over the beta function times the integral from 0 to 1 of y to the alpha 1 minus y to the beta minus 1 dy. Now, using the same trick we used when we did the expected value of the gamma function, notice that this is the same thing as the beta function of alpha plus 1 and beta, okay? So therefore this will be beta of alpha plus 1 beta divided by the beta function of alpha beta. Now recall from the definition that beta of alpha beta is defined to be the gamma function of A, gamma function of beta, over the gamma function of alpha plus beta. Therefore, if we expand this will be gamma of alpha plus 1 times gamma of beta divided by gamma of alpha plus 1 plus beta times the reciprocal of this one, which will be gamma of alpha plus beta divided by gamma of alpha times gamma of beta. But recall also the gamma of alpha is the same thing as alpha minus 1 gamma of alpha minus 1, or in other words, this should equals to this, which is exactly what we used before. So therefore, if we use that, then on the blue part, we're going to end here with alpha gamma of alpha times gamma of beta. And then on the bottom, this is going to be alpha plus beta. This part should be alpha plus beta times alpha plus beta. And then on the right side, there's no need to modify anything. And then just cancel wherever you can. So you can see that this will cancel this will cancel down, this will cancel down. And the answer will be alpha over alpha plus beta, which is exactly what we needed. And in a similar way, you can do the variance. The variance obviously takes longer, but it's the same idea. You have to do the expected value of y squared. You do a similar thing, and then you subtract this from the expected value of y squared, and that will give you the variance. Right, let's do an example. The example says the following: the percentage of impurities per batch in a chemical product is a random variable y with the following density function. Okay. A batch with more than 40% of impurities cannot be solved. So integrate the density function directly to determine the probability that the randomly selected batch cannot be solved because of excessive impurities. So in this particular case, notice how this is technically a gamma distribution, a beta distribution, but it's asking to solve the problem directly. So that's what we will do. So it's asking you to find the probability that y is greater than 0.4, and therefore this will equals to the integral of 0.4 to 1 of 12y squared times 1 minus y dy. And then this is a very easy integral, so this is 12y squared minus 12y cubed. So you integrate, you get 4y cubed minus 3y to the 4 from 0.4 to 1, and you can check that this is 0.8208. All right, so let's say this is, we call this part A. So for part B, let's say you want to find the mean and also variance, or the percentage of impurities. Percentage of impurities. So how do we do that? As I mentioned earlier, you can see that the value for alpha clearly is 3. Why? Because 3 minus 1 is 2. And the value for beta has to be 2, because 2 minus 1 will give you 1. So this one is gamma, sorry, beta, with alpha equals to 3 and beta equals to 2. All right, so therefore the mean, remember, was alpha over alpha plus beta. So in this case it will be 3 over 2 plus 3, which is 5. 3 over 5. So that's the mean. Now the variance, remember, is equals to alpha beta divided by alpha plus beta squared and alpha plus beta plus 1. So in our case, this will be 3 times 2, and then this will be 3 plus 2 squared times 3 plus 2 plus 1. So in this case, this will give you 6, and then this is 3 plus 2, which is 5 squared, and then this will be 3 plus 2 is 5, plus 1 is 6. So this will cancel, so it will be 1 over 25. All right, and that's it for the beta function. As you can see, this is not that bad. You just have to be able to recognize the values for alpha and beta, and that's it. Now let's go to section 4.9. We did this exact same topic in chapter 3, but we did it for discrete variables. So now we're gonna do it for continuous variables. So this is the only difference, that y is continuous. So the definition says the following: if y is a continuous random variable, then the k moment about the origin is given by this, so exact same definition from before. And the k moment about his mean, or the k central moment of y, is given by this. Again, exact same thing. Then what we were really after here is the moment generating function for a continuous random variable is defined to be this, which is again is the exact same definition. Remember, the whole point of getting the moment generating function is that you take the derivative and you'll get the first moment. You take the second derivative, evaluate it at 0, you get the second moment, and so forth. It even uses the same, the exact same setup from last time. Remember, by definition, e to the ty, it will expand it in Taylor series. So first, this is supposed to be the integral from minus infinity to infinity of e to the ty f of y dy. But if we use the same formula from before, e to the x is equal to the sum of x to the n over n factorial 0 to infinity, which is the same one we used in chapter 3. Then this is the integral from minus infinity to infinity of 1 plus ty plus t squared y squared over 2 factorial, and so forth. Okay. So notice this will break it into an infinite number of integrals, but the first one obviously is just the density function, which the integral should be 1. Then the second, it will be t, the integral from minus infinity to infinity of y f of y dy, and so 4. So notice that this will be t times mu 1 prime, which is the first moment. Then you're going to have t squared over 2 factorial mu 2 prime, which is the second moment, so 4. So you take the derivative and set it equals to 0, you will get the moments. Okay, same thing we did before. All right, let's find the moment generating function for exponential function. We can just use the moment generating function derived for the gamma distribution, but let's do the whole thing. So m of t, by definition, remember, is expected value of e to the 2 ty, which in our case this will be the integral from 0 to infinity of 1 over theta e to the ty times e to the minus y over theta dy. Alright, before we integrate, which this is a very easy integral, but it's a good idea to write it the right way. This is what I mean. You have ty minus y over theta. This is the same thing as minus y. Then this is 1 over theta minus t. Okay? Which you can write as minus y 1 over theta minus theta t. So therefore this is the same thing as 1 over theta, the integral from 0 to infinity of e to the minus y 1 minus theta t over theta dy, which is equals to 1 over theta times minus theta 1 minus theta t. You integrate this, e to the minus y, okay, and everything from 0 to infinity. Alright, notice that the thetas will cancel, so therefore this will give you minus if you plug in infinity, or the whole thing is equals to 0. Actually, let me write it like this. You will have minus 1. If you plug in infinity, it will give you 0, and then if you plug in 0 for y, it will give you 1. So this will be 1 over 1 minus theta t. So that's the moment generating function. So therefore, if you want to find the mean, well, remember the mu is the first derivative of mu of t, and then you evaluate it at t equals to 0. Well, m prime is going to be equals to, well, you can rewrite this as this. It will be minus 1 minus theta t to the negative 2 times minus theta, since you are taking the derivative with respect to t. So this is theta over 1 minus theta t squared, and therefore m prime of 0 will give you just theta, which is exactly what we know is the mean. Now we find the second derivative. The second derivative is going to be 2, 1 minus theta t to the negative 2 times minus theta, so it will be theta squared. And you plug in 0, and you should check this. So this just gives you 2 theta squared. So that implies the variance of y, it will be 2 theta squared minus theta squared, which is equals to theta squared, which is exactly what it should be. And that's it. Okay, let's do one more example. So let's say the y is normal with mean mu and variance sigma squared. So we know it's normal distribution. And let's say that the moment generating function is given by this e to the mu t plus 1/2 t squared sigma squared. Okay? So you should give a try to make sure you get this. It's given on the it's solved in the book, but you should try this by yourself. So let's say that we have a new variable. So let x equals to minus 3y plus 4. So let's find the moment generating function of x. So by definition, this will be the expected value of e to the t x, which will be the expected value of e to the t times minus 3y plus 4. Actually, this should be capital letter first. It should be minus 3y plus 4, which is the same thing as e to the 4t. You can take it out. This will be the expected value with the minus 3y times t, which is equals to e to the 4t, the moment generating function of minus 3t. So in our case, all we have to do is substitute the t for minus 3t, and you end up with e to the 4t times e to the mu times minus 3t plus 1/2 to the minus 3t squared times sigma squared, which simplifies to e to the t times 4 minus 3 mu plus 1/2 at 9t squared sigma squared. Notice, this is very important, the x, because of the uniqueness of moment generating functions, the x is actually a normal distribution where the mean is 4 minus 3 mu and the variance is 9 sigma square, which should not be surprising. Why? Because from here, notice that the expected value of x is minus 3, the expected value of y plus 4, which is minus 3 mu plus 4. Remember that y is normal with mean mu and variance sigma square. And also, if this is the case, then the variance of x is going to be 9, the variance of y. Same formula we have used like 400 times now, so it will be 9 sigma squared. So there should be no surprise that this is the case. So this is another way to corroborate this. Okay. And finally, we go to Chebyshev theorem, which is again the exact same thing we did before, except now we're dealing with continuous functions. Remember that the Chebyshev theorem is very useful when you don't have a distribution and need a lower bound usually. Okay? Obviously, you have a distribution, you can find better probabilities, but if you're not sure what the distribution is, Chebyshev theorem is very, very useful, and obviously everything is given in terms of the number of standard deviations. All right, let's try an example. So the example says the following. A manufacturer of tires wants to advertise a mileage interval that excludes no more than 10% of the tires or the mileage of the tires that he sells. All he knows, which means he doesn't know the actual distribution, is that for a large number of tires, the mean was 25,000 miles, and the standard deviation was 400 miles. So what interval would you suggest? All right, so here what we need, based on what the problem is saying, is we need to find a value for k so that the probability that y minus the mean, which in this case is 25,000, that this should be less than or equals to some k times the variance or the standard deviation, that this has to be greater or equals to 0.9. But by Chebyshev's theorem, this is equals to 1 minus 1 over k squared. So this implies that 1 minus 1 over k squared has to be equals to 0.9. And if you solve for k, this will give you 3.1622. All right, so therefore from here we have now that y minus 25,000 has to be between k, which is 3.1622 times 400, and minus k, which is 1622 times 400. So if you multiply and solve for y will be between 25,000 plus 1,264, and then 25,000 minus 1,264. So that means y will be between 26,000 and 23,736. So 90% of the tires should last between this many miles. That's what you should suggest. Now again, this is the lower bound. It could be more than that, but given that you don't have a distribution, this is the best you can do with Chebyshev's theorem. Okay, that's it. So the other questions on this section is just a variation of this. Again, remember the Chebyshev's theorem is just a lower bound. If you have the exact probability and the exact density function, you can have way more accurate results.